Hello everyone, my name is Hu Kaijie. I'm from National Taiwan University, and here's my poster. We try to use the P-diffracted wave to investigate the velocity structure in the D double prime beneath the Pacific region. Okay. Over the past few years, global seismic tomography models show that there exists reverse velocity anomaly in the lowermost mantle, which is we call the D double prime, as you can see the pattern in the figure 1 here. And from a geodynamic standpoint, these strong velocity contrast distributions are long been thought to be associated with a large-scale mantle convection. Thus, to better understand this connection, we try to investigate the velocity characteristics in the lowermost mantle beneath the Pacific region. In this study, we adopt the method that measures the differential travel time residual from P-diffracted wave subtract direct P wave with respect to the 1D prime model. This simple concept of our method shown in the figure 2 and the equation 1, which is here and here. Subtracting the time residual of the direct P wave, we can exclude the shallow velocity effect from the receiver side. Okay, by using these calibrate procedures, we can understand our observations are mainly contributed from the lower mantle velocity effect. However, due to earthquakes occurred unevenly in the world, it's hard to get the direct P wave at the test seismic distance for calibration. Therefore, we turn to collect the numerous test seismic events to build the average travel time model beneath the receivers for calibration, which also can be seen in the figure 6 and the equation 2, which is here and here. But before that, we first discuss two factors that may bring bias to our model, including the depth here and the azimuth of the earthquakes. Because in some shallow events, the depth phase, such as smaller P over P phase, will be too close to the P phase. That may bring bias to our measurement. And here we conduct a discussion by comparing the time window only including the P phase and including both P and smaller P over P phase in measurement. On the other hand, we discuss the azimuth of earthquake because we want to figure out whether the different ray checks in Earth could bring a great impact on the shallow velocity beneath the receiver. And the results of both tests can be seen in the figure 8 and 9, here and here. And you can see that there seems to be consistency in each test, rather than dominated by abnormal feature, suggesting that the anomaly pattern may truly be dominated by the shallow velocity from the receiver side. Okay, so due to the previous test, we made a summation of the results above and gave the average shallow travel time model in the western United States, which is shown in the figure 10 here. And you can see the pattern of our model is similar to the velocity model of 10AO 2012, which is shown in the figure 11 here. Finally, we calibrate the measurement of P-diffracted wave. The result shown in the figure 12 and here. Okay, it shows high similarity with the P wave model because you can see that the advanced travel times, which is green green and dark blue ray trace are distributed at the two sides of ray trace, and the delay travel time is mainly distributed at the center of ray trace. And this is highly similar to the P-wave model. Okay. So this suggesting that the method we developed could robustly depict the velocity anomaly in the lowermost mantle, and in the future we will measure more diffractive events to make the ray trace well cover the Pacific region. And that's about my study. Thanks for your listening.